Good evening, everyone. I was standing outside and ushering people in when a lady who was walking in, I just offered her coffee. And she looked at me and said, "Are you going to deliver the lecture?" Probably she meant that, look, if you are going to, then I really need the coffee. So I'm not delivering the lecture. It's going to be Dr. Eisenkraft. But my job to welcome each one of you on behalf of Azim Premji University. We are delighted to be presenting today's program in our series of public lectures that are organized in our 3 university campus cities, Bangalore, Bhopal, and Ranchi. This is the 273rd public lecture since we started these lectures 12 years ago. This is the second this year. The first was held in Ranchi earlier this week. All our lectures are on our YouTube channel, and I invite you to view them. Public lectures are one of the ways by which the Azim Premji Foundation promotes its vision, and the university promotes its responsibility for public education, bridging the divide between what somebody called the town and the gown. We have an overwhelming response today. We had to close the RSVPs at 390 yesterday afternoon because we had no seats left. Thank you for those who have made it today. I know all of you are here because you are invested in the education and the development of India. You are well-wishers of Azim Premji University. And of course, because of our rock star speaker and the fascinating topic of today. Thank you very much. A bit about the program for this evening. Soon after this introduction, Dr. Eisenkraft will deliver his talk for about an hour. This will be followed by an audience Q&A, and we will close at 8 p.m. A brief introduction to Dr. Eisenkraft. He is a distinguished professor of science education, like Sandhya said, professor of physics, and director of the Center of Cosmic and Math in Context, Center of Science and Math in Context, what is abbreviated interestingly as COSMIC, at the University of Massachusetts, Boston. A past president of the National Science Teachers Association, he has championed project-based learning through active physics and active chemistry. He co-founded and chairs the Toshiba NSTA Explora Vision Awards, engaging over 15,000 students annually for the last 30 years. A fellow of the American Association for Advancement of Science, he has received multiple honors, including the National Science Board's Public Service Award, American Association of Physics Teachers Millikan Medal, and the National Science Teaching Association's Carlton Award. I can say with a fair degree of confidence that Arthur is among the finest science communicators across the world. He comes to India every year around this time, and after his lecture 2 years ago, someone in the audience walked up to me, I think the parent of a young child, and said, "How I wish science was taught like this in India." About the lecture. The lecture traces the evolution of physics from the early mysteries of electrostatics and magnetism to the revolutionary discoveries of Orsted, Faraday, and Maxwell that gave rise to modern field theory. It celebrates Michael Faraday's relentless curiosity and his belief in understanding nature for its own sake. Faraday's work not only redefined our perception of reality, but also demonstrated how fundamental scientific exploration can lead to profound technological innovation. Through his story, that is Faraday's story, the talk highlights how curiosity-driven research continues to shape today's technologies and offers lessons for nurturing inquiry and creativity in science education. Dr. Eisenkraft will now deliver his talk on the beauty of physics from Faraday's curiosity to today's technologies. Please join me in welcoming Professor Arthur Eisenkraft.
Thank you so much for that kind introduction. Thank you all for giving up some of your Sunday night to be here and learn a little physics and education. So what I'd like to start off with is, what invisible things do people believe in? So take a moment. Do you believe in anything that's invisible? And if so, talk to the person next to you and see if you are thinking about the same invisible thing. So just talk for a second. What invisible things do you believe in? Okay, that's enough. That's enough. Can somebody shout out something they believe in that's invisible? Forces. Some forces are invisible, some are visible. Other things that are invisible. God. That's a big. So we have the science crowd and the non-science crowd. Something else? Emotion. Okay. Gravity. Great. Air. Sound. Wonderful. So the question is, how do we know they're really there? And how can we measure invisible things? I remember asking somebody and said, oh, love is invisible. I said, how do you measure it? They said, oh, by the size of the stone. Michael Faraday believed in the invisible. He said, I do not perceive in any part of space, whether vacant or filled with matter, anything but forces and the lines in which they are exerted. So this is an infant's game. And I'm just fascinated by this game because the child's sitting in the high chair and you take a pen and you put it on the high chair and then they knock it over. And then you pick it up and you put it back and they do it again. And then you pick it up and you put it back and they do it again. And they will not tire of this game. They love this game. And I've always wondered, why do they love this game? And it could be that they know they're playing the game with an adult. They know they're controlling an adult. They're getting an adult to bend down and do this. That must be a good feeling for an infant. But it could also be that they're fascinated by this mystery of something falling. Because how does it fall? And when to communicate that to you, let me show it to you a little differently. If I were to take the pen and let it go, and it went shooting over to the wall, and then I said, oh, I take it back from the wall, and I'd say, so what do you think? Do it again. And I do it, this time it goes to that wall. And then I go retrieve it, and I say, do it again. And you would not tire of that. You would not tire of that because it was something unusual. And my claim is that objects falling are just as fascinating, but we've done it for so long, and people said, oh, it's gravity, so we've lost some of that fascination with something. Now, the problem is, there is a problem with this. The problem with this is, how does the pen know which way to go? It's not a surprise. I said, well, let go. Show me with your fingers, you only go down. It goes down. I know that. The question is, how does it know to go down? What is compelling it to go down and not up or to the side? Or what is going on? You say gravity, but that just means it goes down. We can say it goes down, we'll call it gravity. But is the Earth sending little things up saying, come this way, this is the way? How is it communicating to the pen which way gravity is? This was a problem. This is a problem that some people recognized, some people didn't. And so when you try and solve a problem, you say, have I seen this in another context? What's going on? And in fact, when Newton did this, he worried about the attractive force between the sun and the planets. The sun keeps the planets, and the Earth is 150 million kilometers away from the sun. How does the Earth know where the sun is? How does the sun communicate this? Now, lots of people, when Newton was struggling with this, were also struggling with the idea of the sun and the planets. Newton went further. He said the apple or the pen falls to the Earth in the same way that the Earth moves to the sun. The apple falls to the Earth in the same way the moon falls to the Earth. And then, as if that wasn't extraordinary enough, he said, oh, it's not just for planets. The apple attracts another apple. You are attracted to the person next to you. Now you might be tilting over, so just hold on to your seat. But I don't feel that. Because it's too small, and Newton would be too small. Too small, you'll never be able to measure it. 150 years after Newton died, we measured it. So Newton said, we have a law of gravity, we have an equation which describes this. But when they asked him, how does one object communicate with another, this action at a distance? He said, I have no idea. I can't do that. I don't have any idea. I can only go so far. So the question is, why should we even care why the pin falls down or why the apple attracts the apple? And I'll tell you, we care because, for the same reason we care about art or music or theater. It's really quite beautiful and interesting and elegant, and it's somewhat puzzling. Maybe one day it will be useful. So we have something, you probably have it here, I wasn't sure, culturally, the spoiler alert. So if you go to see a movie, and somebody else has seen the movie, let me tell you how it, no, don't tell me how it ends. That's the spoiler alert. Don't tell me how it ends. So, so I was trying to think what's a good spoiler alert. And in the Ramayana, if you've never heard about the Ramayana and somebody says, Ram and Sita get reunited. It's like, why did you tell me that? Why did you tell me that? So the end of our story for today, the spoiler alert for our story is this investigation that we'll have today together will lead to a world that nobody could have imagined. It leads to technologies, the internet, just everything we consider the modern world. So it starts with static electricity. It starts with, in the dry season, you walk on the wool carpet, you touch the doorknob and you get a little shock. Or the clouds do the same kind of thing and you get a bigger shock. And then you can put your hand on a big charged thing and your hair can go up like this. Or I can take two pieces of tape, and I can take these two pieces of tape, and if I separate them like this, now if I bring them, do you see that? Look at that. They attract. Over space, they attract. They know enough to move toward each other. Or I can take it and I can take another one, and let me see if this one works. No, that's attracting. Let me see if this one. And now they're repelling. So a different one, these repel. So that's it. They know to attract or they know to repel. And so people knew about this. People worked on this. So you have attractive force, repulsive force. And again, we say there must be two kinds of things that do that, and we call them top and bottom, positive and negative, whatever it is. And we have rules which tell us about coming together or going apart, and we even have an equation for that, just like we had an equation for gravity. But again, the puzzle is, how can we describe the force? By an equation, but how does one know the other one is there? The same thing, this action at a distance. And then we have batteries, which we know can produce charges and change our world. And then we have magnets. So we know if we take two magnets, they repel, or if we turn them around, they attract. Again, how do they do that? Or I have a compass here, and it tells me that north is this way. And because somehow the Earth is telling it which way to point, the puzzle, again, is how do the magnets work, the action at a distance. So now we get to some interesting ideas: electricity, magnetism, gravity. Orsted in 1820 showed that a current could produce the same effect as a magnet on a compass. See, we're used to the compass just using it when we're hiking. This is north. But if I took a magnet, I have a magnet here, and I could get the compass to move in different directions. So what Orsted did was he was a teacher, and he had left his magnetism or his compasses on the table, and a current went through, and he noticed the compass shifted. And so then he wraps it around a compass like this, and when he wraps it around, if you put a current through there, it will deflect. And so here in the top picture, you have all the compasses pointing north, you put the current through, and now it doesn't get attracted to the current or away from the current, but at right angles in a circle. So that was kind of unusual, but it showed a connection between electricity and magnetism when no connection had ever been thought of before. So Ampere in France Orsted did not do the math, Ampere did the math, and then said, wait, if a current acts like a magnet or can affect a magnet, then I can take a second current affecting like a magnet. Maybe the two currents will attract each other. And in fact, it did, and he figured out the equation for that. So again, the same puzzle, action at a distance. So now we get to Michael Faraday. We'll learn a little more about him, but let me just suffice to say, he's not good at math. Not good at math at all. So he wants to understand this interaction of the north and south, the interaction. And so he says, I'll make some pictures. And he makes these pictures, and he calls them fields. And he divides these pictures, and he says these fields can describe this force of attraction. And the particles, or the other object, will interact with these fields that the picture I've drawn. So he can take the magnet, and he says, here's the magnetic field here, that's what it looks like. Here for a charge, this is what the fields look like. And he does all these fields. And then he says, okay, so if you have a magnet, this is what the field lines look like. And in school, we put little iron filings down so we can see the magnetic field, the reaction of the iron filings to what Faraday said was a magnetic field. And we can do that with a horseshoe magnet as well. And we can do that with electric charges and draw the fields. Now, if you look at this, we know that this north-south magnet and this north-south magnet repel each other. We know they repel each other because north and south repel. Look at the field lines, though. These field lines are to the right. These field lines are to the right. So Faraday said when the field lines are to the right like that, you get repulsion. Forget the magnets. The field lines are causing the repulsion. And if we reverse this magnet, then we have the field lines in opposite directions, and that's what causes the attraction. So there's nothing at a distance. The field is right next to each other. The fields interact, and the fields then get the particles to move. He said, I do not perceive in any part of space, whether vacant or filled with matter, anything but forces and the lines that they are exerted, these field lines. And so here are the field lines from a current-carrying wire. And then if you take that current-carrying wire and you wrap it around a cylinder like this, you get field lines that look like this. And it's like, oh, it's just like a magnet. So there's an electromagnet. And then we have the Earth's magnetic field with the South Pole in the northern hemisphere. So my compass points up toward the north, and we have that. And what Faraday realizes is, oh, if the current can act like a magnet, if we take the current and a magnet and we put them in a certain configuration, then I can get a motor. It'll just keep turning. The battery is underneath, so that's the electric current, producing the current. There's a magnet there. So the electric current is creating a magnetic field, which is interacting with the magnet below it, and it's making it spin. So that's a nice invention, a motor. Faraday did that for us. And then the puzzle came. So Orsted in 1820 said electricity can produce magnetism. And then lots of people said, wait, can magnetism create electricity? We'd love to create electricity. We know how to do it with chemical cells, but we would love to create electricity. Can magnetism create electricity? And it takes Faraday 10 years of hard work, and he does it. He succeeds in finding that magnetism can produce electricity. Now, he expected 10 years, he expected, this shouldn't be hard, I should be able to do this. But in fact, it was there was something happened. He tried something, and all of a sudden there was a little bit of electricity, and then it stopped. Then he turned the circuit off, and he saw it again. Then he turned the circuit on, and he saw it again. But his observational skills allowed him to do that. So let's test our observation skills right now. I'm going to show you a video, and if you've seen it before, no spoiler alerts. If people haven't seen, I'll tell you what happened. Don't do this. So I don't know if you've seen this, but you're going to see a video of students passing basketballs around. Some students wear black shirts, and some students wear white shirts. What I want you to do is count the number of passes of the people with white shirts passing to somebody with a white shirt. So I'll show you the video, and then you start counting to yourself, and we'll try this and see what happens. So we'll do this, and they'll give you the instructions here. Count how many times the players wearing white pass the basketball, starting now. Okay. How many people got more than 5? How many people got more than 10? How many people got 14? That's the actual number. Did anybody see anything else? What did you see? A gorilla. How many people saw a gorilla? How many people did not see a gorilla? Okay. So there was a gorilla. So, I'll show it to you again. I'll show it to you again just so you do. So let's watch it again. Don't count this time. Don't count. The counting's distracting. Just watch the video, the same video, just watch it now without counting. And you can see them passing the ball. Don't worry about how many, they're just passing the ball around, and you were counting before. You were doing such a good job of counting. Some people got 14. And as you were counting, oh, watch. So the question is, would you have seen the current that Faraday saw? Is your observational skill so good? So that's a fascinating video. It teaches us so much about ourselves. It's wonderful to be able to focus and not see things. But sometimes it's detrimental because we don't see things that are important. So Faraday was an incredible experimentalist. He was probably the best of the 19th century, if not of all time. He saw that current. And so he started saying, when the current starts, I get it. When I move the magnet, I get it. If I move the magnet, I get it for a moment. So he said, so what we can do is we can move the magnets, or we can move the rod through the magnets, but you can't do it any which way. You have to cut through the field lines. These field lines, I hypothesize, if you move it a certain way, that's when you get the current. So here you have a good example. So somebody is over here, they're pedaling away, and they're pedaling away so the coil moves between the magnets, and then they have a light bulb so they can read their book. So who was this guy, Michael Faraday? So Michael Faraday, poor family, lived in London, very poor. He had a speech impediment, and so when he was 10, 11 years old, he was bullied in school by the students and by the teacher. And his parents just pulled him out of school, said, you can't be in school. So he stays at home, and then luckily he gets a job as a bookbinder in a bookbinder shop. He's going to learn how to take leather and take all the pages of a book and sew them together to make books. And so he does that job, and he's very good at it. But he starts reading the books. And he reads books on how to speak properly, how to get rid of a speech impediment, how to greet people. Then he starts reading science books, like chemistry books, and he really likes them. And so he says to the owner of the bookbinding shop, he said, in that corner, we don't do anything. Can I use that corner to do experiments? And the bookbinder says, sure, you can do that. And so he starts doing experiments. And now when books are being published, he repeats all the experiments in the book to make sure they're right. In the meantime, Humphrey Davy, the most famous chemist in the world, is going to be in England, and he's going to give a series of lectures. Now, I don't know who would be this famous, but you could not get tickets for these lectures. It was a series of lectures. The line, people in gowns and tuxedos around the block trying to get in to see these lectures. Humphrey Davies was an amazing chemist. He gave good lectures. He was also, as you can see, very good looking. And they said the women swooned when he would give his talks. But anyway, somebody comes to the bookbinding shop and says to Faraday, I have a ticket to Humphrey Davies' 4 lectures. Would you like to go? Faraday said, more than anything. Faraday goes to the lectures, sits in the balcony, watches all the experiments, takes notes, writes them up, binds them in a book, in a leather jacket, gives it to Humphrey Davies. And he said, this is what your lectures are. Faraday is probably 21 years old now. And he said, can I work for you? And Humphrey Davies said, well, what do you mean? He said, I'll do anything. I'll wash test tubes, whatever can I please work for you? And Humphrey Davies says, well, how much education have you had? Well, I only grade 6. How much math do you know? Nothing. He said, no, you can't work for me. So then Humphrey Davies' valet gets into some kind of trouble. They're going to Europe. They can't go. He says, oh, well, maybe that Faraday guy will come. He can take care of me and my wife as we travel through Europe. This is Faraday, who has never left a few, not even a kilometer around from his home. Poor. And he says, yes, I'll come. So he goes to Europe. He meets all these chemists. He meets the person who wrote the famous chemistry book that he had studied. And he's treated well by all these chemists, not treated well by Humphrey Davies' wife, because he's a servant. And anyway, he then comes back, works with Humphrey Davies, and still has a tough time. He's making incredible advances, and yet there are interesting things. So when he's brought the Royal Society, everybody in the Royal Society votes, he's been there 5-10 years now, wants to vote Faraday as a member of the Royal Society. Humphrey Davies said no, vetoed it. He did an experiment, and he told people about the experiment. People in Italy reproduced the experiment, and they published it before Faraday. So he was learning about the politics of science as well. But as I said, the best experimentalist of the 19th century, maybe of all time. But he developed all of these concepts through experiments rather than mathematical equations. And because he had lack of math, he had limited respect. This is the person who invented the motor, the electric generator, and people say, well, you're not really a physicist because you don't do math. People whose names we don't know. Thomson, later Lord Kelvin, said, all the views that Faraday has brought forth and illustrated leads to this method of establishing the mathematical theory, but we need that. We need the math. There was only one person in the world convinced of the reality of these lines of force, and that was Faraday. Faraday would give his own lectures now, 500 to 1,000 guest chemistry lectures. I recommend just looking at the transcripts and the chemical history of the candle. You will fall in love with candles when Faraday tells you all there is to look at in a candle. One thing, he said, I wonder what the shadow of a candle is like. No, a candle makes shadows. He said, no, let's shine the light and see the shadow of a candle. This is the kind of mind he has. Anyway, then he asked, who asks? A lot of you know this or everything so far. Is the electricity I'm producing the same as the electricity in the chemical cells, or is it a different kind of electricity? I would have just been happy it's electricity. He's saying, is it the same electricity? So this is his mind. Oh, this is an apocryphal story. The Prime Minister, Robert Peel, was told about this electric generator that Faraday had done and said to Faraday, so what good is this? What good is this generating electricity? And Faraday said, one day you'll probably tax it. And I just love that because, that's what Peel would understand. So Faraday said, I'm just enjoying discovering these things. I'll leave the value of it, the generate electricity, the usefulness of it to other people. So these are our themes so far. Fields versus action or distance. What happens if somebody has a math deficit? And the value of useless knowledge. Just let's play with these fields. Let's play, and we get motors and generators, etc. So now we have to do a quick aside. Galileo wanted to measure the speed of light. Now most of us, the light has a speed. You know, the idea that you turn a light on, it's everywhere at once, you turn it off. No. There's a joke about that, a very fast athlete. They said, how fast is he? He said, he can turn the lights off and get into bed before the room gets dark. So how do you measure the speed of light? It goes so fast. So Galileo said, oh no, we can do this. So he had a friend on one hill. He was on one hill and his friend was on a hill. They're about 5 miles apart. And so he would have a box and he would lift the box and a candle inside, and then the light from the candle would go 5 miles. His friend would see the light. He'd lift his box, and then the light would come back from his candle, and Galileo would time going out and coming back. Now, we don't have clocks now. He's timing by his pulse. He's timing by a water clock, whatever. But he does that, and he said, okay, it went 10 miles in 1 second. He said, light travels 10 miles per second. You're saying, no, it's faster than that. Galileo knew that. He said, it's going at least 10 miles per second. At least 10 miles per second. So how do we get a better number? Galileo was actually measuring his response time. How fast can you do this when you see somebody do something? So Raymer, sometime later, said, I know, I'm going to do the same experiment Galileo did, but I'm going to get a bigger distance. Not 5 miles, but I'll do 186 million miles. What I'll do is I'll have somebody on Jupiter, and every day at noon on Jupiter, they're going to flash their light. And then what will happen is, when the Earth is on this side of the sun, the light will come from Jupiter, leaves at noon, comes here. But when the 6 months later, when the light goes from Jupiter, it goes all the way over to here, so that should take more time. And it does. And so, how do you get somebody on Jupiter? If you're wondering, how does he get somebody on Jupiter to do this every 12 months? These people are very smart. It turns out that Galileo showed us that Jupiter has moons. And the moons go around Jupiter at a constant rate. And so every time one of the moons comes, it's like the light flashing, and then the light flashing, then the light flashing. So that's what he uses to see the extra time. And what happens is, he comes pretty close to this. He said it takes about 1,000 seconds. So he says the speed of light is about 186,000 miles per second, or 300,000 kilometers per second. And then it's like, well, that's in space. How does it work on Earth? And then Michelson said, I'll do the same experiment, except I have a way to improve it. What I'll do is, instead of having that person on the hill, I'm going to have a mirror on the hill, because then I'll go to the mirror. And then how do I measure the time? Well, I can have a rotating mirror here. So it bounces off this mirror, then this rotates, and if it rotates at exactly the right speed, then this mirror will be down here, and then the light will go this way. And so if I know the rotation rate, I can do that. And Michelson also measures the speed of light, and he also gets 186,000 miles per second. And because Alfred Nobel had died, he also wins the Nobel Prize. So that's the number that we all learn in school, 3 times 10 to the 8th meters per second, or 186,000 miles per second, or so many kilometers. So that was the little interlude. Now, patterns are important. So I just want to, again, I want to make sure we can understand what patterns are and how well we can do this. So what I want you to do is shout out the color when you see it. So let's just practice it, and then I'll do it a little faster. But just shout out the color. Blue, green, red. Okay, good. So now we'll start over. Okay, so you were pretty fast without any practice, so we'll do this. We'll see how fast you can go. Okay, ready, set. Blue, green, red, green, red, green, blue. Very good. I want you to do the same thing now. Just shout out the color you see.
Blue, green, red, green, blue, red.
Good. Let's do it one more time. Shout out the color you see. What happened? What happened? You were so good. It's not hard. It's not hard. Look at the color. Red, blue, red. So somehow patterns are important to us. And since we all can read that pattern, it's just too much. You can't, and you felt it. It was like, right. So we're very used to patterns. So here's another way. Which of these are panes? So you say, panes, what's a pane? Oh, a pane is something that has a mark on its back. So you say, oh, okay, if something a mark on its back, then A, B, C, and C are panes. Okay. Or I could say panes are creatures that have antenna, and then you say, oh, okay, A, B, C, D are panes. Then I say panes have tails, and this one has a tail, this one has a tail, this one. So, and so you have those. So patterns are a big part of science. In fact, all of science is really looking for patterns in nature so that we can do that. And an attribute of a good theory is that we find a pattern, and then from the pattern, we can predict things that we didn't know about, and then they turn out to be true. So now, here's James Clerk Maxwell. Lives at the same time as Faraday, and he reads Faraday's publishing all these notebooks and things like that. And he reads about Faraday's fields. Maxwell's an incredible mathematician. And he said, you know what? I think I can make sense of those field lines in terms of mathematics. And so he looks at this and he says, okay, how do we make electric fields? Well, we can do them from charges, or we can and then we have Coulomb's law, or we can do it from the field lines, and then we have Gauss's law. Those are mathematical principles. Then how do we get magnetic fields? We can do it from bar magnets, but the bar magnets don't have north poles by themselves, so you don't have anything there. And then we come over here, and how do we get magnetic fields from an electric field? Well, we can have a current creates a magnetic field, and we have Orsted and Ampere and Faraday and all those people creating magnetic fields from currents. And then how do we create electric fields? Well, we know we can create electric fields or currents. We can make electricity by moving across field lines. When Maxwell puts all that together, he has this pattern of electric fields, magnetic fields, creating magnetic fields from electric fields, and creating magnetic fields from electric fields. And he notices that there's nothing here. And it would be so much nicer. The pattern would be so nice if he could put something here. And so, can he put something there? Yeah, he can. He figures out what equation should go there. What equation should fit here and here. And when he discovers that, he's saying, so if you had a changing electric field, you could have a magnetic field. And now the equations have a symmetry that appeals to Maxwell. And then Maxwell doesn't do experiments. He does mathematics. But what he found was a changing electric field produced a changing magnetic field. And a changing magnetic field can produce a changing electric field. And he's trying to figure this out. He says, wait. So the magnetic field creates the electric field. Then the electric field creates the magnetic field. I'm not supposed to leave here because of the camera and there are people in another room watching this, but I have to leave for just a second. I'll be back for those. So this way, then 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 this way. And Maxwell says these electric field and magnetic fields, they move across the room. And using the mathematics, he can calculate the speed at which they move across the room. And it's 186,000 miles per second. This is not a coincidence. Maxwell says, oh, look at that. I've never seen that number before. No, we've seen that number before. That's the speed of light. So Maxwell said, I think I know what light is. I think it's an electromagnetic field moving through space. And so we draw a picture like this, and I know that for those of you who are familiar with this, you have the same difficulty I do, but Feynman, the great physicist of the 20th century, said, you know, I go like this, and you think, he can see them. He knows what he moves his hands like he knows. He said, I have no idea. I'm just moving my hands. I have no idea how to picture this. And he said, it's harder than angels on the head of a pin. He said, angels on the head of a pin. That I can imagine big angels and little angels, tiny angels, you know, and they get him on the pin. I got that. The fields I can't do. So I feel better. That if he can't see them, I shouldn't be able to see them either. But wait. If there's an electromagnetic field that moves across, and Maxwell said, that's what I think light is. Look at this, the speed is the same. Thomas Young had done an experiment in 1810 where he measured the wavelength of light, the light we see. And it turned out red light was 700 nanometers and blue light was 400 nanometers, and all the other colors in between were between 400 nanometers and 700 nanometers. Maxwell said, I can't find those numbers in my equations. I can't find why my equations are limited to 400 to 700. But that's all we see. And then he predicts that maybe there's other light we can't see that's less than 400 or more than 700 nanometers. And Hertz does an experiment about 10 years later and discovers those radio waves. And so wait, all of a sudden it's like, there are radio waves, there are microwaves, there are infrared rays, there are ultraviolet waves, there are X-rays, there are gamma rays. They're all just like light. They're all electromagnetic radiation, but they have different wavelengths. And we get to use them for different purposes. So everything we now know about electricity and magnetism and light is in these 4 equations. And when we only had light, this room was filled with electromagnetic waves. Light waves, you know, we go see each other, so the light waves are going everywhere. Now there are also radio waves here, and ultraviolet, infrared, and they're all over this room. So the room just got much more crowded with these fields, these field lines throughout the room. How do we know there are radio waves in this room? Well, if I take a radio and I turn it on, I can hear it. So they must have been here. So we have this. Now, here's the claim. If in the 1800s somebody had said, we need a better form of communication. So prior to 1820, we had oral traditions, people would just shout. We had visual signals, you can see me further than I can shout. We had written language, we had animal messengers, put it on a bird. But then we had the electric telegraph and Morse code. A way to have a wire, and we could send a message along wires. But if we wanted a better form of communication like radio waves and television waves, I don't think we ever would have found them. Because we never would have known to even look. We only found them because Faraday and Maxwell were playing around with these things for the pure joy of playing with them. And then we discovered all of these things. So Flexner calls it the usefulness of useless knowledge. The progress of our modern age and the world of tomorrow depends not only on technical expertise, but also on unobserved curiosity and the benefits and pleasures of traveling far upstream against the current of practical considerations. So our themes, fields at a distance, fields versus action at a distance, math deficit, value of useless knowledge. So what is the value? Well, we have from Faraday's laws, we have electric motors, electric generators. From Maxwell's equations, we now have wireless communication, we have television, we have mobile phones. From quantum mechanics, people struggling to see like, well, how do electrons behave? We now have transistors and integrated circuits and computers. Einstein came up with the general theory of relativity, which could explain why the pen goes down. And he said, and everybody said, it'll be of no use to anybody. Because the reason why the pen goes down also makes clocks go slower if they're far from the Earth. They go tick, tick, tick here, but up there they go tick, tick, tick. But it's only a trillionth of a second difference. Nobody could care less. Oh, that's how your GPS works. If they sent the satellites up to GPS, they wouldn't have worked. They wouldn't have been accurate if we didn't know Einstein's equations. So when they sent them up, they said, okay, they're not working. Turn on the relativity time switch. And now they all worked. So the 2025, just read the Nobel Prize this year, was for work on quantum mechanical tunneling. And that's what gives us cell phones, quantum sensors, quantum computers. And in the future, we have possible quantum computing. We have propulsion systems for space travel. Robert Wilson, who was director of Fermilab, where they study particles. You know, you have to study a tiny, tiny particle, you have to build a big, big machine. And it costs a lot of money. And so he has to go to Congress to ask for money. I need money to study these electrons. And this skeptical senator said, will this help us? And he said, what do you mean help? You know, will it help defend America? And he said, no, it's not like that. He said, you know, but no, I want to give you the money, but you have to tell me how it's going to, you know, defend America. And Robert Wilson just said, this new knowledge has all to do with honor and country, but it has nothing to do directly with defending our country, except to help make it worth defending. So why do we believe in fields? Well, we have direct measurements. We have voltmeters. We can measure them. We can predict, electric fields, magnetic fields, gravitational. Maybe there are gravitational waves in the gravitational fields. And a few years ago with LIGO, we detected the first gravitational waves. It all works so nicely. This field theory, it just makes sense across all aspects of physics. And so because it works so well in different things, we start saying, yeah, I think this is really the right way to do it. Now, we tell all our students, please believe in these electric fields that Faraday made up, and these magnetic fields, and these gravitational fields. But there's a person down the road who for 100 rupees will massage your aura. Don't believe that person. And our students sit in the class saying, well, why should I believe you but not them? And so what we have to do in school is help students understand the difference between fields and auras. Auras, I don't mean to say that I don't think they exist, but if you want to have your aura massaged for entertainment, that's perfectly okay. I mean, I read my astrology charts. It says, Gemini, you're going to meet somebody nice today. I like that. I hope I will meet somebody nice, but I don't say, I'm not going to work because my astrology said, do this. You're going to find lots of money today. Oh, I'm going to quit my job because it said Geminis will find a lot of money today. So it's entertainment, but it can get dangerous when you start letting it control your life. So fields, it has predictive power. We know, look at Maxwell's equations, it predicted all of the radio waves, the microwaves. Auras don't predict anything. We can test it. If the field theory doesn't work, we have to change the theory. If we can't detect the auras, like, oh no, today's a bad day for auras, or it's a little weak today, it's faint. Otherwise, it's usually there. I don't know what you must have a negative aura. We have technological foundations. By the use of believing in fields, we have radios and semiconductors, but there's no perceived benefit from auras that we can measure. So this nature of science is something we forget to do in science. Why is it science? What is not science? What is science? So we have rules and criteria. So fields represent tested and reliable understanding of physical reality, or as remain in the realm of pseudoscience due to their failure to produce empirical support. So now let's look at other things in our education besides the nature of science. When we think about Faraday, he had a very different talent. He didn't know math, but he knew how to do experiments. Unfortunately, if he was to come to my university and say, "Can I study some physics?" we would say, "No, you don't know any math. Goodbye." We would not allow him in the university to take a physics course. If he said his name was Faraday, we're going to say, "Oh, hold on, wait, 1 second." But we wouldn't allow that. And if he did have a job at some place which makes fast food or whatever job he has, and he said to the owner of this store, "You know, you have this space here, can I do some experiments?" He'd say, "No, you can't." You know, those opportunities would not exist. And so how do we make sure that we recognize the talents people have and build on those instead of finding the deficiencies that they have and focus on those? How do we look at the assets that students bring to the table and not the deficits that students bring to the table? How do we respect their way of learning, their learning style? So these are our themes again: action or distance, math deficit, useless knowledge, and science. So I believe that there are Faradays in India now, and they're in some rural community, some poor community, and we have to find them. And we have to find them and give them opportunities so they can show us what they know. And you know, I can tell you too many stories. We see it in India, we see it in America. So we have 2 students who come to the university. They both have the exact same points, scores on the state exams, the exact same. They come to the university. This one comes from an affluent background with educated parents. This one comes from a very poor background. His parents don't know how to read or write. They take their first exam. They both get the same score on the exam. So they came in with the same, they get the same score on the exam. They both failed the exam. This student calls his or her parents, and they say, "Oh, no, I've failed tests also. You have to study harder, speak to the professor, they'll help you learn how to study better." This student has nobody to call, and they say, "I guess they were right, I don't belong here," and leave the university. That's the story in America, it's the story in India. So how do we do that? And we do that by investing in teacher training, by developing better assessments. Better assessments. Not, let me find out what you don't know, but show me, do you know things? Faraday is like, well, I invented these fields. Faraday's not the only one. Thomas Young was not recognized. He was a doctor, not a physicist. Jocelyn Bell discovered the pulsar in 1967. She did not get credit. Her advisor, who didn't do the work, won the Nobel Prize. Lisa Meitner discovered nuclear fission, couldn't find a job in America. Madame Wu did not get the Nobel Prize. Rosalind Franklin, DNA with Watson and Crick, did not get it. So it happens over and over again, and too many of these people are women also. So the question is, what is going on with these fields? So Faraday made up fields. Maxwell found the mathematical nature of them. Einstein made field equations. Now we have quantum field theories. Everything is fields now. So in Alice in Wonderland, the Cheshire Cat says, "Only the smile remains." Alice said, "I've often seen a cat without a grin, but never a grin without a cat." And Faraday said, "I do not perceive in any part of space, whether vacant or filled with matter, anything but forces and the lines in which they were exerted." Faraday, in chemistry, safety lamps, Bunsen burners, carbon chlorides, optical glass, benzene, electricity and magnetism, electrolysis, the Faraday cage, diamagnetic, paramagnetic. He also decided to clean up the Thames, which was polluted, and said this is horrible, and he had a social conscience and worked on that as well. He also tried to debunk pseudoscience and was really quite upset about students who, ignorant of their ignorance, and at the end of all that education, and I say again, there must be something wrong in the system of education which leaves minds the highest taught in such a state. So again, we have Faradays in India today. That's one thing we have to be concerned about, that we don't lose talent. We need any talent we can have. The utilitarian view of education, knowledge for knowledge's sake, no. Knowledge is for useful. What are you going to build with that? Your Constitution, the Indian Constitution talks about having a scientific temper, to have inquiry. But I think we've forgotten about that part. The beauty of physics. Now, we all believe in fields. It also turns out that one of the results of Maxwell's work is physics is all math now. The models aren't what we do, it's the math. And that's what we say the physics is. And distinguishing science from myth. So, Proust and Picasso, the voyage of discovery lies not in seeking new horizons, but in seeing with new eyes. And Picasso certainly got us to see with new eyes. Electricity and magnetism are related. That was Orsted. It's like too wonderful to be true that we found this out. They can become a motor. Also too wonderful to be true. It can become a generator. Too wonderful to be true. Electric and magnetic fields exist. These things he made up, they really do exist. Too wonderful to be true. Electromagnetic fields, light is an electromagnetic field. Too wonderful to be true. Maxwell's equations, electricity, magnetism, light, all one thing. The extended spectrum. Einstein, in the 21st century, showed us that electricity plus relativity gives you magnetism. These things are just all too wonderful to be true, all these field equations. Nothing is too wonderful to be true if it be consistent with the laws of nature. That's Michael Faraday. Thank you.